IEEE Standard 1100, titled Powering and Grounding Sensitive Electronic Equipment, Section 9.34 provides guidance on this matter. It states that transformers serving critical and life safety loads should not be connected to standby power. Emergency power sources serving these loads must be sufficiently large enough to carry the normal as well as emergency loads. This standard finds reference within the National Fire Protection Association's NFPA 70E titled Standard for Electrical Safety in the Workplace. The reasoning behind this requirement stems from the potential for transformers to sustain damage from overloads. In the event of a power failure, the generator may lack the capacity to initiate the transformer, and the critical care equipment would be without power pending transformer repair or replacement. To mitigate this issue, one approach involves employing a generator of sufficient size to power both the transformer and the critical care equipment. Alternatively, a static transfer switch, or SDS, can be used to automatically transfer power from the generator to the transformer during a power failure. Let's delve deeper into these concepts. A transformer is an electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. It typically consists of two or more coils of wire wound around a common ferromagnetic core. The coil supplied with electrical energy is called the primary winding, while the coil that delivers the transformed energy is called the secondary winding. Transformers are used to step up or step down voltage levels, isolate circuits, and match impedances. Now consider the scenario of critical care panels in a healthcare facility. These panels supply power to essential medical equipment such as ventilators, patient monitors, and infusion pumps. The continuous operation of this equipment is crucial for patient survival. Therefore, a reliable emergency power system is essential to ensure uninterrupted power supply during a power outage. Generators are commonly used as emergency power sources in healthcare facilities. They convert mechanical energy into electrical energy, providing an alternative power source when the normal power supply is interrupted. Generators must be properly sized and maintained to ensure reliable operation during emergencies. When selecting a generator for critical care panels, it is important to consider the total power requirements of the connected equipment. This includes both the normal operating load and any additional load that may be present during an emergency. The generator must have sufficient capacity to handle both of these loads. IEEE Standard 1100 recommends against using transformers to supply power to critical and life safety loads from emergency generators. This recommendation is based on the potential for transformer failure during an overload condition. Overloads can occur when the generator is unable to provide enough power to start the transformer, or when the transformer is subjected to excessive current. If a transformer fails during a power outage, the critical care equipment connected to it will lose power, potentially endangering patients' lives. To avoid this risk, IEEE Standard 1100 recommends that emergency power sources be sized to directly power critical and life safety loads without the use of transformers. This ensures that the equipment receives a reliable power supply, even during an overload condition. However, in some situations, it may be necessary to use a transformer to supply power to critical care panels from an emergency generator. For example, the generator may operate at a different voltage level than the equipment requires. The transformer may be necessary to isolate the generator from the equipment, or the transformer may be required to provide a specific impedance match. In these cases, it is important to take steps to minimize the risk of transformer failure during an overload condition. One option is to use a generator that is large enough to power both the transformer and the critical care equipment. This ensures that the generator has sufficient capacity to handle any potential overloads. Another option is to use a static transfer switch, or SDS, to automatically transfer power from the generator to the transformer in the event of a power failure. An SDS is a device that can quickly switch between two power sources without interrupting the power supply to the load. In this application, the SDS would normally supply power to the transformer from the normal power source. If the normal power source fails, the SDS would automatically switch to the generator, providing power to the transformer from the emergency power source. This ensures that the transformer receives a continuous power supply even during a power outage. In addition to these measures, it is also important to properly maintain the transformer and the generator to ensure reliable operation. This includes regular inspections, testing, and maintenance of both the transformer and the generator. In summary, IEEE Standard 1100 recommends against using transformers to supply power to critical and life safety loads from emergency generators. This recommendation is based on the potential for transformer failure during an overload condition. If a transformer must be used, it is important to take steps to minimize the risk of transformer failure, such as using a generator that is large enough to power both the transformer and the critical care equipment, or using a static transfer switch to automatically transfer power from the generator to the transformer. Furthermore, adhere to NEC 710, which states that emergency systems shall meet all applicable requirements of this code. NEC 712 discusses capacity and system design. Emergency power supply shall be available within the time required for the application, but no longer than 10 seconds as per NEC 712A. Ensure that the alternate power source has adequate capacity and rating for all required emergency circuits. Equipment shall be suitable for the maximum available fault current at its terminals. NEC 712B pertains to systems supplied by a generator set. Generator sets must have adequate capacity for all required loads and be equipped with automatic starting and transfer capabilities. They must also be designed to withstand the effects of fault currents. Another critical aspect is grounding. Proper grounding is essential for electrical safety and equipment protection. Grounding ensures that fault currents have a safe path back to the source, minimizing the risk of electric shock and equipment damage. In emergency power systems, the generator must be properly grounded to the building grounding system. This typically involves connecting the generator frame to the building grounding electrode system with a grounding electrode conductor. The size of the grounding electrode conductor must be in accordance with NEC 250.66, which is based on the size of the ungrounded conductors. Furthermore, equipment grounding conductors must be installed in all circuits to provide a low impedance path for fault currents. These conductors connect the metal enclosures of electrical equipment to the grounding system, ensuring that fault currents are safely conducted back to the source. Regular testing and maintenance are crucial for ensuring the reliability of emergency power systems. Testing should be conducted periodically to verify that the generator starts and operates properly, that the transfer switch functions as intended, and that the system can carry the required loads. Maintenance should include regular inspections of the generator, transfer switch, and other components, as well as any necessary repairs or replacements. The frequency of testing and maintenance should be based on the manufacturer's recommendations and the specific requirements of the application. It's also important to keep accurate records of all testing and maintenance activities. These records can be used to track the performance of the system over time and identify any potential problems. In addition to the technical aspects, it's also important to consider the regulatory requirements for emergency power systems. These requirements vary depending on the location and the type of facility. In healthcare facilities, emergency power systems are typically subject to strict regulations to ensure the safety of patients. These regulations may include requirements for generator sizing, testing, maintenance, and documentation. It's important to consult with the local authorities and the relevant regulatory agencies to determine the specific requirements for your facility. Remember, electrical work can be dangerous. Only qualified personnel should perform electrical work on emergency power systems. Always follow safe work practices and use appropriate personal protective equipment, such as gloves, safety glasses, and arc-rated clothing, to energize circuits before working on them whenever possible. Use lockout/tagout procedures to prevent accidental energization of circuits. Verify that circuits are energized using a voltage tester before touching any conductors. By following these safety precautions, you can minimize the risk of electrical shock and other hazards. To summarize, when dealing with emergency power for critical care panels, prioritize reliability and safety. Avoid using transformers directly to power these panels from generators whenever possible, as recommended by IEEE Standard 1100. If transformers are necessary, implement strategies to mitigate the risk of failure, such as using appropriately sized generators or static transfer switches. Ensure proper grounding, regular testing, and adherence to all applicable codes and regulations. Remember, the well-being of patients depends on a reliable emergency power supply. Always prioritize safety and quality in the design, installation, and maintenance of these systems. Consider too that NEC 517/30 discusses essential electrical systems for healthcare facilities. These are categorized as life safety branch, critical branch, and equipment branch. Understanding the specific requirements for each branch is crucial for ensuring patient safety. For instance, the life safety branch provides power for illumination alarm systems and communications, whereas the critical branch supports specialized care areas and selected critical equipment. The equipment branch powers major equipment necessary for patient care. NEC 517/30 code delineates the criteria for transfer switches. Transfer switches must be automatic and designed to prevent the inadvertent interconnection of normal and emergency power sources. This is a crucial safety measure to avoid backfeeding and potential equipment damage. The location of the transfer switch is also critical. It should be readily accessible for inspection and maintenance, and protected from physical damage. Regular inspections of the transfer switch are essential to ensure its proper operation. NEC 517/35 describes the essential electrical systems performance criteria and testing requirements. This section mandates periodic testing of the entire emergency power system, including the generator, transfer switch, and distribution system. The testing should simulate a power outage and verify that the system can automatically start and supply power to the essential loads within the required time frame. Records of all testing activities must be maintained for future reference and regulatory compliance. Moreover, the generator itself requires meticulous maintenance. Regular servicing, including oil changes, filter replacements, and cooling system checks, is vital for ensuring its reliability. Fuel levels must be monitored and replenished as needed. The generator should also be equipped with alarms to alert personnel to any potential problems, such as low fuel levels, high temperatures, or system failures. Remote monitoring systems can provide real-time status updates and allow for prompt response to any issues. Another important consideration is the coordination of overcurrent protective devices. These devices, such as circuit breakers and fuses, must be properly coordinated to ensure selective tripping. This means that only the device closest to the fault should trip, minimizing the impact on other parts of the system. Coordination studies should be conducted to determine the appropriate settings for these devices. Regular reviews of the coordination study are necessary to account for any changes to the system. Surge protection is also a vital component of an emergency power system. Surges can damage sensitive electronic equipment and disrupt critical operations. Surge protective devices, or SPDs, should be installed at the service entrance and at downstream panels to protect against voltage transients. The SPD should be properly sized and rated for the expected surge currents. Regular inspections of the SPD are necessary to ensure their continued effectiveness. Furthermore, consider the impact of harmonics on the emergency power system. Harmonics are distortions of the sinusoidal waveform that can cause overheating of equipment, misoperation of protective devices, and interference with communication systems. Nonlinear loads, such as electronic devices and adjustable speed drives, are common sources of harmonics. Harmonic filters can be used to mitigate the effects of harmonics. A harmonic study should be conducted to assess the harmonic content of the system and determine the appropriate filter requirement. Finally, remember to document all aspects of the emergency power system. This includes detailed drawings, equipment specifications, operating procedures, and maintenance records. The documentation should be readily accessible to authorized personnel and should be updated as needed. Regular training should be provided to personnel responsible for operating and maintaining the emergency power system. This training should cover all aspects of the system, including its design, operation, maintenance, and troubleshooting. By following these guidelines, you can ensure that your emergency power system is reliable, safe, and compliant with all applicable codes and regulations. This will help to protect patients, staff, and visitors in the event of a power outage.